Assalamu alaikum wa rahmatullahi wa barakatuh. So this is lecture 2 of the Control System Engineering 1 course. This is based on chapter 2, Modeling in the Frequency Domain. Actually, we'll start from whatever we are learning in the last class. Basically, the 6 steps of our designing and analysis of the control systems, the steps that we are going to follow. So today actually we are going to look at step 4 from the schematic diagram, how to obtain the block diagram. So developing the block mathematical model from the schematics of the physical system, this is what is our objective. So how can it be done? Basically it can be done. So what we are trying to do is actually we're looking into this step 4, and for this one we have 2 methods. The first 2 methods that we can go for. The first one is transfer function. And which is supposed to be in a frequency domain. Okay. And the other one is in the state space representation. So state space representation, and that will be actually in time domain. As we already said in the last class, this will be covered in chapter 3. And it is not part of our course. So only if you're interested, then we're going to go into that one. Otherwise, we'll be trying to follow only this one, which is the content of this chapter, that is the transfer function approach, which is the modeling in the frequency domain. Okay, so how can we actually obtain mathematical model, that is the methods, how to obtain the transfer function. So basically once you have the schematic diagram of the physical system, so from the schematic diagram, so you have to go through fundamental physical laws, Then you're going to get is your transfer function of the system. Transfer function. So what is meant by fundamental physical laws? If it is an electrical network, so for electrical network, we represent it by Ohm's law, fundamental Ohm's law, or Kirchhoff's current voltage law. Okay, so very fundamental rules. So fundamental laws that we have to apply, and through which we are going to find out a equation that will actually represent the system. Then that equation is in general a differential equation. So the differential equation is difficult to deal with the differential equation. That is why we'll be taking the help of the Laplace transformation to obtain the transfer function. So in case of the electrical network, these are the fundamental rules we are going to apply, of fundamental laws. But if it is a mechanical system, in case of the mechanical system, then it has to be Newton's law. So Newton's forces, summation of the force or the summation of the torque. So those, like in Kirchhoff's law, what do we have? Summation of the current in a node, or in case of in a loop, summation of the voltages in a loop has to be equal to 0. So this sort of fundamental law we have to apply to find out our transfer function. Okay, so what is our bottom line? Bottom line is to find out a relation between the input output based on these fundamental laws. So a simple version of it can be an dn by dtn ct plus an minus 1 dn minus 1 by dtn minus 1 ct plus goes on up to a0 ct should be equal to bm dm by dtm. This is your reference plus bm minus 1 bm minus 1 by dt m minus 1 rt goes on up to b0 rt. So here your C is actually our control variable, or simply output, and R is actually reference or input. And what are A and B? A and B is the coefficient of the differential equation. So A is the coefficient of the output variable or control variable, and the B is the coefficient of the input or the reference. So one of the problems with this differential equation is the input, output, as well as the coefficients are all over the equation. So we cannot explicitly separate input, output, as well as the coefficients. So differential equation is not easy to deal with. So because of that, what we want to go for is we want to have a system like this where actually we can have our input, output, and the system will be defined separately. So this will be our input. This is our system, and this is our output. Okay, so reference, so that is why R, and this is a control variable, that is why it is C. In some literature or some book, you're going to find that this is actually also can be expressed by YT, and this can also be expressed by XT. So in this book, we are going to follow R and C, as well as the small letter is for the time domain, and the capital letter is for the frequency domain. So basically what we are saying that we don't want a differential equation to represent the system that in which the input and the output as well as the coefficients are all over the equation. Rather, we want to have something like this where you will have the system as separate, the input is separate, and your output is separate. It may happen that your system may consist of multiple subsystems. In that case, we can also have something like this, cascaded form maybe. So this is your subsystem 1, this is your subsystem 2, this is your subsystem 3. So maybe multiple of them is available. So, and then finally this is your input and output. So in case of the subsystems, each of them will have their corresponding transfer function. So they're in the cascade or in multiplying form. So you just have to multiply them together to find out a reduced block diagram like this. Okay, so this is how it works. This is what is preferable to us so that we can easily deal with, separately deal with our input, output, and the system. So one thing we have to be careful in case of this differential equation. So order of this differential equation, here you have the nth order. Now in this side you have nth order. So in general, nth order is greater than m. Okay, so now the question here is, if these are too high, more than maybe third order, fourth order, so then the system is becoming so large, the representation of the system is of very high domain, high order. So basically because of that, it is difficult to find out the solution of the system, or to have the insight of the system. So that is why one thing we generally don't discuss in this class, but we should also go for we have to apply some simplifying assumptions, so that only the relevant dominant parameters are being taken into consideration, so that we can actually reduce the order of the system. So the more and more you practice, based on that, those ideas, these simplifying assumptions will be clear to you. But in this class, we are not going to go in detail. Actually, it will definitely come with examples, more and more examples that you practice and try. Based on that, simplifying ideas will be clear to you as well. Okay, so now how can we actually convert the differential equation to a transfer function? As we already said, that we have to take the help of the Laplace transformation. So the differential equation of your system, you have to obtain differential equation. Then through the Laplace transformation, we are actually going to get our transfer function. So how we are going to get that? Before going to that, we actually want to review the Laplace transformation a bit. So the Laplace transformation. So by definition, Laplace transformation is basically you have a time domain signal, ft, and you want to get a frequency domain signal, fs. Fs is the Laplace variable. So the way to get it is basically the Laplace transformation. So mathematically, if you write, then what we have is Fs. If you take the Laplace transformation of Ft, then you're going to get Fs, and which is just an integration over 0 minus to infinity ft e to the power minus st dt. This is the definition. So why 0 minus? There is a big question to answer. So, but in simple, basically 0 minus ensures that if you have a discontinuity or initial condition that actually contains discontinuity, then at times we have to apply that very close to 0, but not exactly that discontinuity that we are considering. So because of that, it is 0 minus. But in general, you are going to, what you're going to get is something like this. As general term is 0 to infinity, then your ft it is going to minus st dt. Okay, so also one of the some of the aspect of the Laplace transformation, those are actually complex. We are not going to go in detail, like the region of convergence or abscissa of convergence. So this sort of thing may complicate the ideas, but if you want, we can actually discuss those as well. But our main focus is to take the advantage of the commonly transformed functions, and we are going to take help of them to find out our differential equation converted. With the help of those, we will be trying to convert our differential equation to our a transfer function. Similarly, the inverse Laplace transformation. So inverse Laplace transformation. So according to the formula, what we have is inverse Laplace transformation. So basically this time we are trying to find from Fs we are trying to find out the ft. So 1 by twice j, twice pi j, integration of sigma minus j infinity to sigma plus j infinity. Then you have fs e to the power st dt. And now if you do that, then you are going to get is actually ft. Along with that, you will also have ut. So ut, what is ut? Ut is basically unit step function. So ut is having a value 1 if it is if t is greater than 0, and if it is 0 if t is basically lesser than 0. It should be equal here as well. Okay, so why actually you are giving fs but you are getting ft and then multiplied with this one? So ut is nothing but we are actually omitting the past values. We are just considering the present value and the future values. T greater than t is equal to 0 and greater than 0. But if you have any past value, actually we are trying to avoid those. Okay, so because of that, ut is being multiplied with that one. It is always there, because in control we always consider the present and the future, but the past values we don't consider. Okay, now let us try to find out the Laplace transformation of some basic function. So say unit step function, we have to find out the Laplace transformation of the unit step function. So a unit impulse function. So unit impulse function is unit impulse function. Okay. So unit impulse function is delta t equal to 1, 0, where it is 1, t equal to 0, and elsewhere, that means if t is not equal to 0, then actually the value of the impulse is 0. Now here, but in some literature, especially in control, you will see that it will be also mentioning that it is for t greater than 0. Because in the control literature, because of the fact that actually we are not at all considering t lesser than 0. So t not equal to 0 is also true for in general case. But in control, because we are not interested about negative values of t, so basically we can also write t greater than 0. Okay, so what will be the Laplace transformation of your impulse unit impulse function? So what is the ideal definition of del t? So actually we also have to look at that one. So ideal definition of the del t is basically limit sigma tends to sigma is a very small number, f sigma t. Okay. So this is the definition. And what is f sigma t? F sigma t is basically 1 by sigma for t in between 0 and sigma, and elsewhere actually it is 0. So this is your ideal definition of the impulse unit impulse function elsewhere. Okay. Okay, so now if we have to apply the formula for the Laplace transformation, so what do we have to do? We have to go for something like this: Laplace transformation of delta t is going to become Laplace transformation of the limit sigma tends to 0 f sigma t. So we have to apply this formula to figure out what is happening in case of what will be the Laplace transform of your unit impulse function. So we have to know what is actually the Laplace transformation of that function as well first. Okay, and also we have to consider about the limit. So since the limit is dealt with only sigma, not t, whereas the Laplace is actually dealing with the t, so we can actually take the limit outside. So limit sigma tends to 0, Laplace transformation of f sigma t. Okay, so what is Laplace transformation of f sigma t? That is what we have to calculate first, then we can come back to this equation. So just keep it is a note as a 1. We'll just keep it 1. We'll come back to 1 again. So what is the Laplace transformation? Later on we'll apply the limit. First of all, try to find out what is the Laplace transformation of f sigma t. So just apply the formula. The formula says 0 to infinity. Then you have to apply your function. So function is f sigma t, then e to the power minus st dt. Okay, so now f sigma t has two parts. F sigma t at 0, it is actually 1, and elsewhere it is actually 0. So we can write something like this. So from 0 to sigma, very small length sigma, we actually have that 1 by sigma e to the power minus st dt, and the rest square from sigma to alpha, sorry, infinity, we have actually magnitude is 0. 0 e to the power minus st dt. So what we are going to get here is, because 1 by sigma is a constant here, so 1 by sigma can be taken outside, and this parameter is definitely going to become 0 multiplying with the 0. So what we were left here with is e to the power minus st by minus s. Then you have to apply the limit 0 and okay. Okay, so now if you just simplify, you can take s outside, so 1 by epsilon s. Then we have, if you apply epsilon e to the power minus epsilon s, it will be replaced by epsilon, so epsilon s divided by actually minus e to the power 0 is 1, so minus 1 divided by minus 1 here, that minus 1 here. Okay, so this is what we have. So finally, what you can write here is 1 minus e to the power minus epsilon s by epsilon s. Okay, so now this value we have to put into that equation. So what we are going to get here is Laplace transformation of your unit impulse function is becoming limit epsilon tends to 0, 1 minus e to the power minus epsilon s by epsilon s. Okay, so next is what we have to do is basically e to the power minus epsilon s, that we have to expand that using the Taylor series. So we have to expand this one using the Taylor series. Okay, so what we know is e to the power x is basically equal to 1 plus x plus x squared by factorial 2 plus goes on x cubed by factorial 3. Okay. So here, if we assume that our x is equal to minus epsilon s, then what we can write is something like this. So it can also be in summary, you can write something like this: a summation of n equal to 0 to infinity. Then you have x to the power n, x to the power n, and then you have factorial n. So similarly, since we are taking x equal to minus epsilon s, we can also expand using this formula. So basically, Laplace transformation of delta t is going to be something like this: limit epsilon tends to 0, 1 minus summation of n equal to 0 to infinity. Your x is basically minus epsilon s, so minus epsilon s to the power n divided by factorial n. So that will be divided by epsilon s. Now, before applying the limit, we have to simplify the thing. So limit epsilon tends to 0, 1 minus, now if we expand it, 1 minus epsilon s by 1 plus. Rest of the thing actually you don't have to use, so you can actually keep it as a loop equal to n equal to 2. So we're just taking the first two, n equal to 0 and n equal to 1. So rest of the thing is still in the summation. So minus 1 to the power n epsilon s to the power n divided by factorial n. Okay. So definitely 1 and 1 is getting cancelled out. Then you have epsilon divided by epsilon. So basically it will become 1. So limit epsilon tends to 0, 1. Actually, you can avoid the putting the limit here. So directly you can actually write 1 minus something, because in the 1 you cannot apply the limit, isn't it? So you can skip one line. So you can write 1 minus limit epsilon tends to 0. Then you have the summation n equal to 2 to infinity. Then you have minus 1 to the power n. Then you have epsilon to the power epsilon s to the power n minus n. You can keep it n, no problem. Then you have divided by factorial. You have 1 epsilon s, as well as you have factorial n. So 1 epsilon s will be deducted here, so it will be n minus 1. So bottom line is, if you apply the limit here and you are having epsilon here, so basically this whole term is going to vanish. So what is left is your result 1. So the Laplace transformation of unit impulse function is basically becoming 1. So if you want to physically understand what is happening, how we actually applied that function f epsilon t, what is actually f epsilon t? It is nothing but represented by a square with epsilon. So the horizontal width is epsilon, and your height is basically 1 by epsilon. Is it okay? So once, what is happening actually, if your epsilon is actually tends to 0, so this length will be actually reducing. And if you just multiply these two, then you can see that the magnitude is at 0, and the magnitude will almost become 1. So this is why it is called delta t. Okay, so delta t, when your limit that you are applying, epsilon becomes 0, tends to 0, then your f epsilon t is becoming actually delta t. This is how actually it is being derived. Now, what is the point? Actually, why I try to derive this one is basically to let you know that how complicated it is to go for some fundamental, even for some fundamental function, to figure out their corresponding Laplace transformation. And actually, it may take more time than to use, you have to spend more time on Laplace transformation than rather than doing actually learning your main control engineering. So that is why we mainly are not going to uh, apply this Laplace transformation method directly. Rather, we are going to take the table. This is basically your table 2.1. We'll try to memorize this one if possible. Table 2.1. Actually, the way we are going to apply, very soon you are going to remember what is the content of this table. But even if you fail to remember, don't worry. I'll try to provide you the table in the exam so that you don't have to remember. But I'll actually encourage you to try to remember this. And as well as your table. So as you can see, we have done a lot of calculation to figure out what is the Laplace transformation of del t, which is 1. You can also show what is the Laplace transformation of ut, then time function t ut. Ut is always there, as I said, that this is the function that is used to specify the fact that we are actually not taking any term lesser than 0. So the positive values are actually ignored. So let's try to apply these ideas for a few problems or solving things. Then it will be more clear how to actually apply those. So let us go for example 2.1. Example 2.1 is basically applying the Laplace transformation method, the integration method to figure out. But in general, we will not go into these methods in detail. Rather, we prefer applying this table. So, example 2.1. So, example 2.1, what it says is you are provided with a time function that is a is a magnitude e to the minus at, and then ut. So this is your time domain function is given. You have to find out the corresponding frequency domain function. So you have to apply the Laplace transformation. So basically you have to apply 0 to infinity. So we are not writing 0 minus because of the fact that it is not a discontinuous function. So that is why we are writing ft, then e to the power minus st dt. So simply put the value of the ft here. So what you are going to get 0 to infinity. E to the power a, e to the power minus at, e to the power minus st dt. So take the summation of the exponentials, then you have a e to the power minus s plus o t dt. Okay, a is a constant, so you can take it outside your outside the integration. So a, then you if you take the integration of this one, so what it will become is e to the minus s plus a t divided by minus s plus a. Okay, then you have to apply the time value from 0 to infinity. Okay, so if you apply infinity, it is going to become 0. Okay, so and if you apply 0, then it will become 1. So basically 0 minus 1. So minus 1 will be multiplied with this one. So what you're going to get is basically a by s plus a. So this is your Laplace transformation of your a e to the power minus a t, small a t. So, but you don't have to do that because it is already there. So once you see e to the power minus a t, you can easily say it will be going to be a 1 by s plus a. So if you have any constant, so that constant will be actually replaced here, something like this. So most of the time, we're actually going to take the help of the table other than actually directly applying the Laplace transformation. Okay, so let's take the help of the table to solve your example 2.2. Example 2.2. So what it says is you have to find the inverse Laplace transformation. Now Fs is given. Fs is actually 1 by s plus 3 whole square. So s plus 3, so it is related to this one, isn't it? S plus something, so s plus 3. So it is related to e to the power minus 80. So we can say that in the result we will have something like this, e to the power minus 3t. Okay, because of this parameter, because this is related to this one. Now you have square. So s is squared, the whole something is squared. So we already dealt with something. Now square is coming from here. So basically it means whatever the function you have, that has to be multiplied with the time function. So basically you can say that this is your function, then the unit step function that we have. So this is how, by looking at the table, without actually doing the inverse Laplace transformation, which is a complex process to do, how we are actually going to apply the table to find out the corresponding time domain or frequency domain results. Okay, so next is partial fraction expansion. It is also, I believe you already know, but just a review of the things. So on the next topic that we're going to discuss is partial fraction expansion. So we are going to discuss 3 different cases here. So actually, if your function is a complicated one, so in that case, it's difficult to use Laplace transformation or inverse Laplace transformation. So if you have a complicated function, so you need to convert it to a function of sum of simpler or smaller terms. Okay, so if you have a large function, so if you have a large function with your numerator and denominator, which is a large number of components you have. So instead of that, what you have to do is you have to make it small components, something like this. Okay, so this is our idea. So that idea is actually known as partial fraction. So a large complicated function is actually truncated into sum of small functions so that we can easily apply the Laplace transformation on those small functions. So let us start with a numerical example. The first point is whether you have to decide whether the order of ns is higher than order of ds. If this is the case, order of and if this is higher than that of ds, in that case you cannot apply the partial fraction. Partial fraction expansion cannot be applied. What do you have to do? Always the order of the ns has to be lesser than that one. If your order of the ns is higher, then you have to divide it first, then make the order of the ns lower, then you can apply the partial fraction. So you have to go for the successive division. Say in a general case, say fs equal to, we have something like this, s cube plus 2s squared plus 6s plus 7 divided by s squared plus s plus 5. So definitely this is your numerator ns, this is your denominator, so order of the numerator is higher, so you cannot go for partial fraction. What you can go is, what you have to do is we have to divide the numerator with the denominator. So basically s cube. I know you already know it, but still, since it is the initial classes, and for some of you, it may be difficult, I'm not sure. So that is why I'm just showing the division as well. Okay, so if it is S, I just multiply it because you have to just match this one with this one so that you can obtain this one. Very simple idea. So S cube plus S squared plus 5S. So now if we subtract, what you're going to get is S squared plus S plus 7. So basically taking 1 should be enough. So S squared plus S plus 5. So basically we have 2. So 2 is your remainder and S plus 1 is your quotient. So basically what we are going to get is Fs equal to, we are going to get S plus 1 plus 2 by S squared plus S plus 5. So now if you want to find out Ft, definitely S, how can we find out S? How can we find out 1? 1 is very simple. The Laplace transformation of the delta function is 1. So definitely we can say that this will be delta function. So S, what is S? S is, we can take help of the table here, the other table that we have here. Okay, so S is basically for derivative terms. So basically this is where we have S. Okay, so derivative of a function can give you S and then some initial condition. So we're just assuming that we don't have any initial condition because it is not specified. So, and what is that function? We already figure out the function for this one. So it has to be the same function. So it has to be d del t by dt. Then now this is the one that needs to go for the partial fraction. So we have to take the Laplace, the inverse Laplace transformation of this one. Okay, inverse Laplace transformation of this one will give you the time domain function S squared plus S plus 5. Okay, so if the order of the numerator is higher, then you have to go for this approach. But if the order of the numerator is not higher, then you can go for the partial fraction. So for the partial fraction, basically we have 3 cases. Again, it is just a review because of the first class. First mathematical core class, I should say. So first case is case 1. Case 1 is basically real and distinct roots. So you have both the root is real as well as and distinct. Okay, so in that case, how to deal with it? So we'll first try to give one example, then we'll try to generalize the formula for that. So say we have Fs equal to 2 by S plus 1 divided by S plus 2. So now, as you can see, you have 2 roots. One is S plus 1 and one is S plus 2. So we have to go for the partial fraction to separate these two. So basically we have to write K1 by S plus 1 plus K2 by S plus 2. Okay, so what is K1? Idea is simple. What you have to do is the whole function is this one. So this whole function Fs, the formula is very simple. Fs has to be multiplied with corresponding value. If you want to find out the K1, so K1 corresponding value is S1, so you have to multiply with S plus 1. Then whatever the value you have to set S equal to that corresponding value, that is S tends to minus 1. So now 2 by S plus 1, S plus 2, S plus 1. Okay, so S plus 1, S plus 1 are getting cancelled out. Now S tends to minus 1. So basically 2, and then minus 1 plus 2 is basically 1. So basically you're going to get 2. So K1 is 2. Idea is very simple. K2 is become same thing, Fs times S plus 2. Then you have to set S tends to minus 2. So if you apply that, 2 by S plus 1, S tends to minus 2, and it is becoming, in the denominator is becoming minus 1, so it is becoming minus 2. So what is our Fs is becoming now? So Fs is becoming 2 by S plus 1 minus 2 by s plus 2. So if you want to find out the corresponding, this is the partial fraction that we are talking about, the case 1. And now if you want to find out the time domain function, then you have to take inverse Laplace transformation. So inverse Laplace transformation will give you ft equal to, you know what is this? This is nothing but delay. So 2 e to the power minus t, 1t, minus 2 e to the power minus 2t. And don't forget, there is always ut. Okay, so this is how to deal with the scenario like that. Now, if in general, how to deal with the generalized case. So in case of the generalized scenario, say we have a general equation like Fs equal to numerator s by denominator s equal to lots. So because we don't care about the numerator, we just try to find out the denominator. Denominator may have n number of poles, s plus p1, s plus p2, so goes on up to s plus pm, and finally s plus pn. So these are the number of total n number of poles you have. What is our target? Our target is to isolate them. So basically k1 by s plus p1 and k2 by s plus p2 plus goes on up to km by s plus pm, and finally kn by s plus pm. How to find out? The formula I already said that kn should be equal to the fs that we have, that has to be multiplied by s, because km is related to this pole, isn't it? So s plus pm, it will be multiplied with the corresponding pole. Then you have to set basically the s tends to that particular value, so minus pm. So this is the generalized way to do it. Okay, so how many doesn't make any difference, as long as they're real and distinct, you can apply this one. Okay, now go for example 2.3. A differential equation is provided, d square y by dt square plus 12 dy by dt plus 32y equal to 30t ut. So your input is actually unit step input, and y is your output. So what they want to find out is to figure out what will be the solution of this equation, and you have to apply the Laplace transformation. So using the Laplace transformation, basically you have to find out the solution of this one. They also given that because we have a derivative terms are actually related to the initial values. So if you try to use the actual formula, so there will be a lot of initial values. But for simplicity, they have just said that all the initial values are 0. So you can easily take the Laplace transformation. So if it is order of 2, then it will be simply by s square. So s square ys. If it is order 1, 1th order, then it will be just s. So plus 12s ys, then plus 32y. And the Laplace transformation of ut is nothing but 1 by u, 1 by s. So simple idea. Just using that table, we are just putting the value. Again, if you are not convinced with me about the derivative differential terms, then let us look at the table where it has got. Yeah, this is here. It is. So as you can see, the number of the derivative terms here, if there is nth number of derivative terms, first for nth order, it is always s to the power m fs. Then whatever the rest of them are, actually those are initial values, 0 minus values, initial values. So the problem says that initial values are 0. So this is actually already 0. So what we are doing here is whatever the order of the differential equation, we're just putting that many number of s there. So if it is d square y, then we are saying s square ys. Okay, so now okay. So this is where d square, so second order, so that is why s square. This is first order, that is why s, and there is no derivative term, so that is why it, as it is. So now you just take common, so s square plus 12s plus 32 ys equal to 32 by s. So ys is becoming 32 by s into s square plus 12s plus 32. So that can also be further divided. So what we are going to have is s plus 4, then you have s plus 8. So ys have three terms, three roots. We can actually separate them as a summation. So using the partial fraction. So what we are going to have is k1 by s plus k2 by s plus 4 plus k3 by s plus 8. Okay, so now how to find out the k1? Very simple. K1 is 32 by the whole function. From the whole function, that particular term will be just vanished. So basically s plus 4, s plus 8, and that particular value of s we have to set, and that will give you 32 by 32, that is 1. And what about K2? K2 will be basically 32, then s plus 8, and you have to set s equal to minus 8. Then you're going to get is basically, this is going to become minus 8, and this is plus 4. So minus 8 plus 4 will be multiplied together. Okay. Okay, so this will give you, I think, oh, sorry, we are actually applying the second term also. So it has to be 4. So it will be 4. So it will be minus 4, and it will be minus plus 4. So basically 16. So minus 16. So basically it will be minus 2. Similarly, K3, you can figure out K3 will be 32 by this is for 8. So basically s plus 4 will be there. So now you have to set s tends to minus 8. Now it will actually become 32 by 32 again. So basically 1. So this is your partial fraction expansion. So ys is becoming 1 by s minus 2 by s plus 4 plus 1 by s plus 8. So inverse Laplace transformation will give you yt equal to 1 by s is nothing but 1 unit step. So minus 2, this is the delay, e to the power minus 40. Then you have plus 1, e to the power minus 8. And with the whole thing, you have ut. But as you know, ut will always be there. So you can actually omit the values in advance. In the later chapters, we are going to see that most of the time we actually don't put ut. Okay, so this is your case 1 where your roots are real as well as distinct. Then this is how you have to treat with them. The second case is slightly complicated, the case 2. So the case 2 is basically the roots are real and repeated. Real and repeated. Okay, so again, let's go with an example. If s equal to say we have 2 divided by s plus 1, then you have s plus 2 whole square. Okay, so for this particular case, how many roots we have? We have a single root at -1. So, okay, so at -1 we have simple pole or simple root, and at -2 we have multiple, that is actually two poles or two roots. So how to find out the partial fraction for this one? So this is what we are going to see. Now, you have to actually expand it as k1 by simple one. Then you have to have k2 by s plus 2 whole square and plus k3 by s plus 2. Okay. So the multiple poles has to be actually separated in this way. So we'll also see the generalized one, don't worry. So once you have this one, finding k1 and k2 is same as before, so you don't have to bother about it. So finding k1 and k2 is same as before. What will be the value of k1? K1 will be 2 by s plus 2 whole square, and then you have to set s tends to -1. So this will give you the value of k1. So similarly, what will be the value of k2? 2 by s plus 1. Then you have to set s tends to -2. That will give you -2. So K1, K2 is not a problem, but the problem is to find out the K3. For K3, what do you have to do? This equation 1, actually, you have to differentiate with respect to, first of all, you have to multiply both sides with the repeated roots. So the equation 1 will be actually multiplied by the repeated roots, that is s plus 2 whole square in this case. So what you're going to get is 2 by s plus 1 d equal to k1 s plus 2 whole square divided by s plus 1. Then you have k2. Then you have s plus 2 k3. Okay. So first step is to the equation has to be multiplied with the repeated roots. This is the first step. The second step is you have whatever the equation that you are having, the equation 2, you have to differentiate this equation with respect to s, equation 2. Now that will give you, if you want, you try it by yourself. I already solved it by myself, but there are too many steps. So you do it by yourself, try to verify my answer whether it is okay or not. So if you do that, what you're going to get is -2 by s plus 1 whole square equal to k1 s plus 2 into s divided by s plus 1 whole square plus k3. Okay, so after differentiating with respect to s, then you have to set s tends to -2 because that the repeated root that we have. So in this equation now, we actually have to apply s equal to -2, and then if you apply s equal to -2, this will be -2 plus -2 plus 2, so it will be this term will be vanished. So we'll be having left with only this one, -2 by 1 equal to 0 plus k3. So eventually k3 will also be -2. So what we are going to get is finally is something like this, fs equal to 2 by s plus 1 minus 2 s plus 2 whole square, k1 and k2, which was found using the same previous formula. So -2 s plus 2. So now if you take inverse Laplace transformation, then you're going to get ft. We are omitting the ut, so what you got left is 2 e to the power minus t minus, because of the square term here, you have to have a t, then the delay e to the power minus 2t, then you will have minus 2 e to the power minus 2t. So this is how you have to find out if you have a repeated root. So let us now look at more generalized approach. In the generalized approach, we may have R number of roots. So say fs equal to ns by ds, and which is, say, we are finding the ds as something like this: s plus p1 to the power r. So at minus p1 we have r number of roots, then rest of them are actually simple code. Then p2 goes on up to s to the power s plus pn. Okay. So at p1 we have r number of roots, and the rest of them are actually distinct poles or roots. So how to deal with it? So we have to find out the partial fraction in a way like this. So say k1, the first k1 divided by s plus p1 to the power r plus k2 divided by s plus p1 to the power r minus 1 plus k3 s plus p1 r minus 2. So it goes up to kr divided by s plus p1. Okay, then rest of them will be just coming as it is. So say kr plus 1, because already we have r number of coefficients. So s plus p2. Okay, s plus p2 plus goes on up to kn, maybe s plus pn. Okay, so this is your generalized version. So how to find out? Procedure is again same. The procedure is K1 you can easily find out, but K2 to KR, if you want to find out, then what you have to do, you have to multiply the equation with the repeated roots. So basically, if this is your equation 1, so what you have to do, you have to multiply the equation 1 with repeated roots, that is s plus p1 to the power r. Then you have to differentiate it to find out the corresponding value of K1 to KR. So then you have to set the value of that corresponding is equal to P1 as well. So K1 or generalized one will be basically 1 by I minus 1 factorial. Then you have D I minus 1 divided by ds I minus 1 fs. Okay, so fs into basically that multiplying factor that we have, that is s plus p1 r. Okay, then you have to set s equal to p1. So what is the value of I? I is basically here is 1, 2, 3, goes up to r. And also, just for a question, the factorial of 0 is basically 1. You may have to apply it for the first value, K1. Okay, so this is a complicated generalized formula, but in general, we don't have to go for more than 2 poles, but it is always better to know the formula, because it may happen that you're stuck with it. So if you know the formula, then you can easily apply the formula to find out what will be the repeated roots. So you can actually practice something like this. Say one example, you fs equal to 32 by s plus 6 s plus 10 cube. So what will be in the corresponding ft you have to figure out. Okay. So you can practice something like this so that it can give you a better idea how to do it. So I think it is almost 1 hour elapsed. We actually have covered so many things. So let me finish it here and let us continue with the case 3 in the next class. So we are still in the partial fraction thing, and case 3 of the partial fraction, which is complex or imaginary roots. That one will start in the next class, inshallah. Okay, see you up to that thing, inshallah.